Next, I would like to introduce you to Tony Robertson, who is going to be, and I believe Tony is up next. Sir, are you with us? Tony?
Yeah, I'm here.
I just metered you out. Let me do an intro for you, if that's okay. For anyone who doesn't know.
I've got an intro in the beginning of my presentation.
Oh, okay. Well, yeah, wonderful. I would say go for it then, sir. And thank you for joining us and thank you for presenting.
How do I do my screen thing?
So at the bottom, there is a green screen share button.
Okay. And I just hit this one here, yes.
Perfect.
Okay, now let me get that started. Okay. I go by two names, by Glen and Tony. Some people know me by Glen, some people know me by Tony. I write most of my papers in Glen, but this is kind of my background. I got BS in physics and math and Master of Science in operations research. I worked for the government for about 39 plus years, 31 of them with NASA, retired in 2018. In 2008, as an outside at NASA activity, I formed the Institute of Advanced Studies in the Space, Propulsion, and Energy Sciences and held a conference with that, which Tom mentioned earlier, the Space, Propulsion, Energy Science International Forum. We closed that down in about 2014. We stopped having the forums, and I'm going to blame part of it on Paul because he started his own conference and pulled about half of our people away to go to that one. And then there was a bunch of other ones that started around the same time, so we kind of shut it down. I really would like to start doing something again, but we'll see. I've got some books. This Gravity Superconductors, a book with Giovanni, which I'll show you the front of that in a minute. And then these other ones are just the conference books that we have. I've got numerous papers, but little of them are in journals and about 11 patents. I worked on the NASA superconducting gravity team. This is me. I'm much younger then. This is probably in the around 2000 time frame. There's Ning Lee over here. And this is my boss, Witt. Ron Kozer and David Nover were from the science directorate, which Ning actually came through Witt to me, and we were forced to bring the science directorate involved into there. It's the large disc we made to do. I don't remember if it was 11 inches or 12 inches, but it was something like that. And then this is the only paper that was done that had my name in it. There's a second paper with David Nover and Ron Kozar, but they didn't offer to put any of us on that. The book I did with Giovanni Monese, I'm the second editor on that book. I did 2 chapters in that book. If you want to know why a superconductor can create a gravity wave, read my chapter. And this second chapter is sort of related to what I'm going to present today. It sort of has some earlier information in it, but it's completely different than what I'm going to present today. And what I'm presenting today then is what I'm calling quantum gravity as a quantum work field. If you go up to ResearchGate, you can find this paper, and I just updated it so you can go look at it. It has a lot more material in it than what I'm going to present. Basically, all I'm really going to present today is the gravity portion of it with a little bit of acceleration towards the end, but it's basically just a model. So it starts from somebody else's theory, but it's just a model. And I think anybody that has any device that creates an acceleration, I can model that under this model. I firmly believe that. And basically how it starts is under this paper by Curry and Weltman called Computing Cosmology. They have this term which they call a thin shell. They call it a thin shell mechanism, but this is the equation they have in their paper. And everything on this page you can actually use to derive this form, which what I've been using since I started writing papers on this. Basically, what you have here is an energy scale factor, which has the cosmological constant in it and the Planck length in it. This is the reduced Planck length. It's just the Planck length with 2 pi, I think, in it. This is the density of the object you're talking about, which say would be the Earth. The radius of the object you're talking about would be, and the atmosphere that's around it. In chameleon cosmology, they have a coupling factor which follows the atmosphere, which I removed because it's going to always be 1. And even in their papers, they set that to approximately 1. But I've added a second one in it because you need it for what I'm doing in this paper. But basically, the chameleon cosmology model is you have a mass, and around that mass there's a thin shell, which they give by this term, which comes from this equation here. So the mass has a density, and the mass has a radius that feeds into the formulation for this thin shell. And this is the thin shell thickness. This coupling factor can be calculated 2 ways. You can just take, if you look at my paper, I have what I call an energy density formula, which comes out like this in the paper, which then condenses down just to pi Planck's, reduced Planck's constant, speed of light over this thin shell to the 4th power, which I show in the paper is actually equal to 1/2 the density of your object times the speed of light squared. And so then if you take this thin shell, put it into this form, throw it all together, you calculate this this coupling factor that I put in. And you can do that a different way by taking this energy density formula and this thin shell thermometer, recalculate the gravity formula into a density equation, and then throw in this equation into the density, you get this guy. Then if you throw this equation into for this guy, then you can recalculate this coupling factor, and it comes out to about 0.691. And coupling factors are kind of something important in what I'm doing here, so I'll keep going. Gravity in a thin shell, you take what I just showed you, basically you can calculate gravity in terms of this thin shell thickness to the 4th power by using this formula. And I had a model that I've been doing for about since 2009 that I've been calling chameleon cosmology, that I knew had to fit into this, gravity had to fit into it, but never could figure it out. But I was listening to Tom Valone's coffee conference a year or so ago, and a guy named Fleming gave me an idea that helped me work this gravity equation out to look like this. But basically what I was missing was actually this term in the long run. So I have to throw out a keto to Fleming. From the standpoint of quantum gravity, this energy density has to have an associated wavelength. So what you can do from this equation here is this thickness, then this thin shell thickness actually is the wavelength of the energy that's actually in this shell, thin shell. And so you set the thickness to the wavelength to the formula I showed before, which is related to the density of your object, which then basically says that the chameleon thin shell is an energy shell of quantum fluctuations. And I wrote gravity in terms of this energy, so it comes out to be the 4th power of the quantum energy in this shell around the objects, which I said, therefore, gravity mediated by the quantum energy in the object's energy shell of quantum fluctuations, which is the same thing as a thin shell. Now, if you look at the energy in there and the wavelengths from the standpoint of a mass fluctuation, you can write the quantum equations in each term and come out with a mass that's in here that comes out to this equation. And in the paper, I showed that for the Earth, the wavelength is about 7 × 10⁻12 meters. And it yields a mass of about 1.96 10⁻30 kilograms, which is approximately 2.15 times the mass of an electron, which kind of indicates that the quantum energy fluctuations at the surface of the Earth is an electron pair type phenomenon. kind of repeat this in a different way. But in other words, the electron pair interactions about atoms at the surface of objects result in the teeny fluctuations of elementary particles emanating from the surface of the object. And the reason I say they're elementary particles, they can't be electrons, otherwise the Earth would be glowing, basically, if you put these fluctuations of electrons on the surface. So it has to be something fluctuating that's not charged. Okay. Now, if you take what I just did before, you can put this mass in terms of the density by this equation, throw that back into the gravity equation. And so you end up having an equation that's related to the mass that's vibrating at a wavelength here, the wavelength you can calculate. My camera is actually in the way of everything here, so I can't see things. But anyway, you can rewrite this energy density using this into this equation, which is equal to this. When you do that, you end up with the mass times c, which is a momentum, which then is equal to this, which is then equal to the Planck length over the wavelength, which is actually the equation for quantum momentum, which kind of means the thin shell carries momentum. And I, just as a side note, if you let this mass be 2 times the mass of electron, and you have to have some kind of coupling constant in here, which for the Earth, it comes out to about 1. So it's really not that much of a factor in here. I also want to know this assumes no charge. There's no charge in any of these equations. And also, if you take this frequency for the Earth and put it into the wavelength equation, into the frequency equation, it comes out to be about 10 to the 7th terahertz frequency that these masses are oscillating at. Now, if you take a step back in time and look at the universe where it's just one mass, then you can take that wavelength equation as increments away from the mass, as a density of increments away from the mass, which if you keep the mass constant, it's just a function of the radius of the mass, so that you end up having at every increment out to infinity, you can calculate these wavelengths within these rings. The blue line I'm indicating is the random fluctuation of elementary particles emitted at the surface. But anyway, I've inferred this in my paper as all these rings out to infinity as an energy shells of quantum fluctuations field. So it basically just says so it's a field. And when you take that as being a field, then it infers that space-time is a time-wise compilation of all these rings of energy from all the masses in the universe over time that are muddled together, muddled energy shells of quantum fluctuations. And you can see that if you take this form of the equation, which I showed you earlier, which has this wavelength in it, and divide it up into one side that is the energy shells of quantum fluctuations, the other side basically is your space-time, which is inferred by the gravity in here, which this equation is just really the gravitational constants over the density of your objects. I note that there is no indication that these energy shells are the same thing as vacuum energy. It's more to say that they actually are telling you that space-time has these energy fluctuations associated with it. And because of that, you can model this field as gravitational gradients or as your space-time field. You just have to take the equation and put it back into whatever these equations generate these and come up with the same thing. Now, from my comedian acceleration model I've been doing for years, which is a differential thin shell model, and I'd apply this to this new gravity information that I have. What you have is wavelengths on either side of your mass that are different. They're differential from each other, and it's this differential that causes your gravitational force. And you can see some timeline history. I reported this model in 2009, At that time, it wasn't called a chameleon acceleration, but in 2017, I brought in the concept of entanglement. And what the entanglement means is that because these thin shells actually go out to infinity from a mass and mix with other things and form this field, then they're entangled to the field on both sides. But their entanglement is different. So you can write the gravity equation in this way, where you have a forward and aft wavelength that are different sizes, and then if you take these equations and replace these densities with a coupling factor, which is your coupling factor to your field, where your aft coupling is greater than your forward coupling, and throw it back in here, and you get this equation. And if you assume the coupling is due to the density of the object, the gravitational object, say the Earth, then you throw it in this equation. It pops out like this if you assume that the aft coupling minus forward coupling is 1. Okay. And you can take this same model and apply it to the acceleration of the universe, where basically you're assuming that your couplings to the universe on the forward and aft sides are different. And I actually did this model way back in 2009. So it's not a new model to me, but maybe you guys haven't seen it. But you can, if you assume the gravity equations is acceleration equation, then you can say the acceleration on objects in the universe is given by this equation, where you have the coupling on either side, and you use the density of the object that's being accelerated, because in far space, the gravitational field of the object accelerating is greater than that of the universe gravity attraction. So you come out with an equation like this with the coupling factors, and the only thing you can really assume is that the aft's greater than the forward, so it's greater than 0. And you can actually apply this to the rocket model too. This EX assumes the exhaust gas, so the exhaust gas being accelerated out through the nozzle of a rocket is actually causing an increased density that's greater than the changing density of the rocket, since it's losing propellant. And in the chameleon acceleration model, I showed that this changing density in the nozzle is a function of the acceleration of the exhaust gas over the gravity field that you're in, such that this becomes much larger than the change in here, which from the density equations that I gave earlier, the wavelength associated with the nozzle side is much smaller than that in the forward side. So from the acceleration equations that I have before, you get an acceleration going towards space due to the change in the couplings because you're now coupling to this density instead of the Earth's density, and so you're moving forward. And you can look at, I'm not going to get into the equations, but if you look at this paper is where I actually formulated the new model for my chameleon acceleration equation, which came from looking at the propulsion equation, the propulsion model. And then you take those models I've shown you and just put it into a quantum field type of model. Then this is highly exaggerated because this thin shell around a mass is tiny. It's you're on an order of 10 to the minus 12 for the Earth. But what you have an accelerating object is that the wavelength on the aft side gets smaller than the wavelength on the forward side. So your energy on the aft side is greater than the energy on your forward side, which you can interpret it as the aft side contraction, energy contraction, and the front side, the energy expansion, which makes it look like the field is expanding on the aft side and contracting on the forward side. And I put these arrows in to interpret the momentum that's in these shells, which you can, to change the momentum, you can get by this. The longer the length, the wavelength is, the smaller the density by this density equation here. So you have a greater momentum pushing on this side than you have on this side. So if you change in momentum is actually positive because of that. But if you take this model and the other models I would interpret it, then you have this change in quantum fluctuation contraction of these shells here, which looks like a field expansion, which looks like space-time expansion on this side. And on the other side, you have the quantum fluctuation expansion, what looks like a field contraction, what looks like space-time contraction. So basically, these two models are the same. So what I'm saying is that a warp field is created about an accelerated object at any speed. And that's pretty much for the model. I just wanted to make a point that Mr. Michael Boyd pointed this out last time, that the solar flares were slowing radioactive decay. If you assume that these solar flares are somehow changing or putting a ripple in the quantum energy that's going from the sun to the earth and oscillating the your energy shell about the earth, then you can, the thesis can be that these energy ripples associated with solar flares cause a vibration in the Earth's energy shell that results in a probability change in emission of radiation. However, if this is the case, there should also be a ripple in the Earth's gravitation at the same time, and in other quantum systems that are associated with it, due to the fact that there's some kind of electron pair interaction with this. And there actually is some papers out there that talk about a seasonal effect on these Josephson junctions that they used as they call it a Zener reference. And you can see that in this ripple here, the peaks occur about every March 1st over this 5-year period that they measured it. So what this Josephson standard is, a Josephson junction. So it's a superconducting Josephson junction that they're using to have a 10-volt standard that they use to calibrate Zener diodes, I think is what it's all about. And I have this paper, but I don't know where it was published. I also have a presentation associated with this if anybody wants it. But here's another paper that's related to this. You want to see it. And this is basically everything I was going to present today. There's a lot more information in my paper. I even do some acceleration models in the back end of my paper. The inertia model I do in my paper probably fits the asymmetric capacitors that Hector is working on. So if you want to talk about this model related to that, I don't think there's anything that accelerates that can't fit this model. So if you have something, some device you're getting some kind of effect out of, then I probably can model that under this model. But you'll have to determine what these coupling factors are from what you're doing. So if you've got magnetic electric fields in here, they play into that coupling factors for your fields.
Oh, okay. So Tony, that's just about it for your presentation then, or?
Yeah, I didn't want to get it too long into it. I really didn't want to get into the acceleration models too much because it might be doing some stuff with somebody with that. So I didn't want to go totally public, but all that's in my paper if you want to go pull my paper down off of ResearchGate. The experiments that I want to do aren't mentioned in the paper though.
Ah, okay. Well, if that's it, why don't we do an applause for you and then do a Q&A session? And actually, we have another guest as well, but let's do the Q&A session first. So let me put it on. Let me see. I will stop screen share for you. Okay, let me put it on gallery view. Everyone, please put your hands together. Tony Robertson. And Tony, thank you very much for presenting. For anyone who doesn't know, Tony, I mean, you're a tremendous figure in this area. That was why I wanted to do an intro. So you were a co-chair at the STAFE conference, right? And then you were really one of the pivotal figures at NASA involved with the Poklonov experiments. So your name was in the news for years.
Well, I've been keeping a low profile because I worked at NASA for years. Now I don't work for NASA. I don't care anymore. So, you know, I hear people talk about a lot of people who I work with, you know, specifically Ning Lee seems to be more popular than I think she should be. But I've talked to Poklonov. I mean, he came over and we talked to him. So I didn't know about what he was doing. In fact, we heard about the impulse experiment before he even wrote the paper on it. And what a lot of people don't know is he didn't really write it papers. It was Modenese that wrote the papers, and he wrote them from talking to Poklonov. So the papers that are written are actually secondhand information. So I don't know if you can believe it all, but I do believe that what he saw was probably true, even though it does sound ridiculous. But because there's a lot of, like I said, if you go back and look at my paper in that book, I can tell you why he can see a gravity effect from the superconductors. Whether he did or not is I don't know. He's also doing some experiments with something else now where he's seeing some kind of effect. So, but I don't know much about that. I think you said something somewhere about it in the past or something. But yeah, I've been looking at this stuff since well before 2000, probably since the 70s. I've been looking at all this stuff, and I know a lot of the people you'll talk about. You know, Woodward's work. In fact, I've modeled Woodward's work under the model I've done and show that it matches it pretty well. I've met a lot of the people you talk about, like Hal Puthoff and all those people. I don't know them well, but I've talked with them. And there's quite a few people in these pictures that I know. Hi, Mike. Hi, Ben.
Yeah.
And Hector's gone, but I was in the room at NASA when he came and showed his device that Campbell stole. In fact, you might need to delete what I'm about to say, but when the lawyers called me about Campbell's work, I told them they stole it from Hector Sarando and that he should at least mention Hector Sarando and their group in his patent, and he didn't. So,
yeah. Well, and be careful because I can't edit this as well as usual. So.
Okay, I don't care if you leave it in or not, but because like I said, I told the patent people that. So.
Yeah. Well, Tony, thank you for presenting.